Hey everybody, this video is made to give you some high-level, big-picture intuition about the differences between the three common types of interest: simple, compounding, continuous, and just some intuition about interest in general that will be delivered without getting bogged down in these nitty-gritty calculations. Now, with interest, you usually have this scenario where you start off with some amount of money, principal, which we're going to call P. That'll be sitting there accruing interest at a rate which we'll call R for some amount of time, which we'll call T, or X, actually, for the purposes of Desmos. And in the case of compound interest, this might be compounded by a factor of n. Now, there's some nice compact formulas for how much money you'll have after, some amount of time X has passed. And for simple interest, that compact formula is P times 1 plus R times T. For compound interest, that is P times 1 plus R over N. And all to the power of nt. And for continuous interest, that compact formula is P times E, which is a particular number. It's about 2.7, all to the power of RT, or PERT, as some people like to remember it. Now, these are nice formulas and all, and if you plug specific numbers into them, they'll happily spit you out more numbers back. And in that sense, they're perfectly functional for calculating how much money you'll have after some amount of time. What they don't do well, though, is show you some fundamental differences between these types of interest, right? It's not very easy to see, just by looking at formulas and equations, why the difference between these three matters so much. That's where a visual tool like Desmos can be very helpful. So I'm going to type all three of these formulas into Desmos, and we're going to look at the behavior of the graphs that we get out of them. So first we'll start with simple interest, which will be typed in as P times 1 plus R, and we're going to use X instead of T because Desmos only accepts X as the x-axis variable, and we're going to plot time against money. And you see that when we type that in, we get this option for add slider, right? Now what that does is it allows us to adjust the specific values that we want to put in for P and R. So I'm going to add all the sliders, and you see that the default is that P gets set to 1 and R gets set to 1. So I'm going to keep P at 1 for simplicity. I'm going to set R to something more reasonable, like maybe 10%. Great. And now you see that we've got this little curve here. Now I'm going to do one more thing here to this equation, and that's that I'm going to round down X to the nearest whole number, because simple interest only disperses at regular intervals, right? It doesn't increase every little second. You sort of get lumps of money, right? Every year or every month or every day, however often it disperses. So I'm going to type floor, which just means rounding down. And you see that we get this little stepped-like behavior, right? Just to indicate that we get the money in chunks. All right. Now I'm going to type in the compound interest formula, and that's going to be P times 1 plus R over N. You see here that this gives us an option to add N as a slider, which I'll do in a moment. We'll take that, we'll raise it to the power of N times X, since we're using X for T. And once again, we're going to round down NX to the nearest whole number, because the compound interest only disperses, just like simple interest, at these discrete intervals, right? Once every month or year or day. And so once we add in our slider for N, we get another graph for compound interest. Now immediately you see this fundamental difference between compound and simple interest coming out. It's not just that compound interest gives you higher numbers, although that's certainly true. It's, great for someone who's investing in compound interest. It's that the character of the curve for compound interest is different than the character of the curve for simple interest, right? Simple interest gives you this nice straight line, whereas compound interest has this curving up behavior, right? There's a fundamental sense in the way that compound interest is better than simple interest, and it's because of this exponential behavior of the money as time passes compared to the linear behavior. In fact, this is so strong that I could decrease this principal down to, a little fraction of a cent. No matter how little money you start with, compound interest will eventually go past simple interest, right? Bear in mind here that with compound interest here, I can start with $0.0000001 compared to $1 for simple interest, and still eventually surpass simple interest, just because the character of the curves is different. This is how, deep that these differences run between these two kinds of interest. Anyway, another difference between these two kinds of interest is that the step size, right, on this graph in compound interest depends on the value of n. So if I start bumping n up, right, if I make the compounding factor 2, this step size for compound interest is now half the size that it was before for simple interest and for when n equals 1. And the more I bump up this step size, the smaller these steps become, the closer and closer they get together, and the closer this growth looks like to being a continuous curve. Now, it's not actually a continuous curve, right? Even if I bump up n to absurd values, it's still going to be discrete, right? It's still going to disperse at regular intervals. But you can make the intervals arbitrarily small, depending on how big you want n to be. So that's another difference between simple and compound interest. Now that actually brings us pretty nicely into continuous interest, which, as you can imagine, doesn't really have this step-like behavior. If we type in the formula, p times e to the power of rt, or rx, my bad, you see that continuous interest is smooth. At any given point, you're going to be increasing ever so slightly, rather than getting your money in little chunks as you do for compound and simple interest. Another point is that for the same principal, time, and rate, etc., continuous interest is always going to be slightly better than compound interest. It's not going to be a lot better. The difference isn't nearly as drastic as it is between simple and compound interest. But no matter how big I make my compounding factor, right, I can make this 1,000,000. I can still zoom in really, really close and eventually see that any moment now, that compound interest is ever so slightly worse than continuous interest, just by this minuscule, pretty much insignificant bit, but it's still slightly better. Anyway, now that I've highlighted the differences between these three kinds of interest visually, I want to play around with the values of our principal, time, and rate, just to show how differences in those things will impact the character of these three curves. So once I finish zooming back out, I will show you that. Let's bring this compounding factor back down to 1, just so the differences between continuous and compound are visible again. And then we're going to start playing with our principal to start. So you can see hold on. You can see as I'm dragging this principal higher and higher, the initial value of our money, right, increases once t is 0, and these curves all of them slope up, without changing the sort of ordering that we established between them. Simple is still less than compound by a drastic amount, and continuous is still slightly better than compound. Now if I bring my principal back down to 1, and I start playing with the rate, you see a similar thing, right? Playing with the rate has a much bigger impact than playing with the principal, but the ordering is still preserved. Simple is still worse than compound by a lot, and continuous is still better than compound, just by a little bit. And I definitely encourage you to go on Desmos yourself and, sort of recreate the setup and play around with the sliders. But until next time, that's all I have for you today. See you all in the next video.